Hey guys, so the problem that we'll be discussing today is from the recent CodeChef Starters 6 and the problem name is Chef's Homework Dilemma. So the difficulty level for this particular problem is easy medium and its prerequisites include a good knowledge of C++ STL for implementing, of course, or segmentary, and you need to know dynamic programming or you need to have some experience with dynamic programming. So let us directly now proceed to the problem statement. So starting off with the problem statement, chef's school semester lasts for n days. Okay, so chef's teacher gives the students some homework every day and it is compulsory to turn in the homework by the very next day. So chef knows that the number of minutes needed to complete the homework on the ith day is hi. So basically we have been given an array of n numbers which contains the number of minutes chef needs to spend each day doing his homework. So chef hates his homework and wants to spend the minimum amount of time possible in doing homework. Now, luckily, he has a few tricks up his sleeve, so chef can hack the school records on any day to make it show that the assigned homework is complete. So, to avoid suspicion, chef will not hack the records strictly more than k days consecutively. So basically, what chef can do is he can skip doing homeworks for say k days consecutively and not more than that. So let me just show you a quick example. So let us say we have 1, 3, 2, 4, 5. So these are the minutes required on each of the 5 days, and let us say k is equal to 2. So over here, the best solution for chef, where he has to spend the minimum possible minutes in doing his homework, it will be, let us see. So he will do the homework on the first day, then he won't do the homework on the next couple of days, and he will do the homework on the fourth day. So the summation here is 5. Do we have a better solution over here? If you see, what chef can do is he can choose to hack the records on these 2 days consecutively and these 2 days consecutively. So here he has to just spend 2 minutes doing his homework. So here 2 is the optimal solution. Now I think we have seen the problem statement and the sample case. So let us quickly proceed to the solution approach. So let us start with the solution approach. So first we will discuss again a small example to just make the problem statement clear. So here what we have to do is let us say we have k is equal to 2 over here. So we need to choose such days such that so we do not skip more than k consecutive days and the total sum of chosen days is less than or it's minimum. So here if you see the optimal solution is choosing 35 and 449. Then we can skip 45304, we can skip 601, we can skip 490, we can skip 452 and 190. Now, so what we did over here basically, so for calculating, so we can divide this approach into a sort of a dynamic programming problem. So how can we do that? So now let us consider dp of I. So what will we define dp of I to be? So let us consider dp of I to be the optimal solution of solving the homework for the first I days, along with solving the homework on the ith day. So dp of I will have the answer of solving the homework on first I days along with solving it on the ith day, right? So now let us see what this means exactly. So this means if chef solved his homework on the ith day, then it is obvious that he skipped the k number of days before this day, right? So the last time he solved his homework could have been back on I minus k minus 1th day, right? So now if you see the optimal solution here is, so here chef solved his homework on the ith day, and then before that he directly solved his homework on the I minus k minus 1th day, right? But in case of a situation like say we have some days in between this where the homework could have been lesser than both of these. So we can define the concurrence relation something like this: dp of I will be equal to a of I. So a of I is basically the homework assigned on that day, so the ith homework submission time, and a of I plus minimum of dp of j. So what is dp of j? Where j is equal to from I minus 1 to from I minus k minus 1 to I minus 1, right? So the k days before the ith day, or the k plus 1 days. So k plus 1 days before the ith day. So why do I say k plus 1 days? Because in these k plus 1 days, chef will do his homework at least once, right? Because he can skip only k days. So chef will do his homework at least once in these k plus 1 days. So basically we get this recurrence relation through our explanation that I just showed. So now let us see how we can use this recurrence relation and how we can frame our answer. Now let us try to work this DP on this case that we discussed before. So as we know, we had this case and we had k is equal to 2. So now for the first k plus 1 numbers, dp of I will be the same as a of I, because there is no k size sliding window before that, right? So here we will just write 601, 35 and 45. Now from here what we have to do is we have to check the three size sliding window. So we have to check the k plus 1 size sliding window. Size sliding window minimum. So sliding window minimum needs to be checked. Now what is the minimum for this element in its previous k plus 1 sliding window? So basically the minimum of 601, 35 and 45. So it is 35. So for this dp of I will be equal to 304 plus minimum of dp of j, which is 35. So it is clearly equal to 339. Now we will check for this element what is dp of I for this. So it is 449 plus minimum of this. So it is again 449 plus 35. So it is, I think, yeah, 484. So 484. Now let us see what is the minimum, what is the dp value for this element. So it is 452 plus 45. So 452 plus 45, it is 497. And finally for the last element, let us check what is the dp value. So it is 190 plus 304. So I think it will be 494. Am I right? Yeah. So the dp so this is our, basically this is our dp array, or this is our dp array. So now how do we calculate our answer from this dp array? Now we know that the ith element gives us the optimal answer up to that day, including the homework done on that day. So now if you carefully see, if we start from here, so this will give the optimal answer for all the elements considering that homework is done on this day. So we can consider that we can skip k days, right? So we can consider the last k plus 1 the last k plus 1 elements in this and find the minimum from it, because if we choose this element we still have 2 days after it. So if we do homework on this day, then we can skip 2 days after it. So this is how it works, that we choose the minimum of the last k plus 1 elements. So in this case, the last k plus 1 elements are 484, 497 and 494. So it is clearly the answer here is 484. And now if you remember, the answer was actually 484 when we saw a dry run of this test case, because we had selected 35 and 449 as our values that on these days chef will do his homework. So indeed what we have to do is basically minimum of dp of n minus k minus 1 to dp of n. Am I right? Oh no, sorry, dp of n minus 1, because we are using zero based indexing. So minimum of dp of n minus k minus 1 to dp of n will be our answer, which here is 484. So yeah, this was the overall solution approach. And now the tough thing over here is to implement it, because see, I will show you. So dp of I is equal to a of I plus minimum of dp of j, where dp of j is basically the minimum among the last k plus 1 elements. So now this is basically a problem where we need to find the sliding window minimum. So now sliding window minimum can be done, so this can be implemented using, so we can use segmentary, but I somehow found segmentary a bit complicated, so I decided to implement it with C++ STL like data structure called double-ended queue. So let us see how we can implement this sliding window with double-ended queue. So now let us see how we can find the minimum of a k plus 1 sized sliding window using double-ended queue. So let me just give you a brief introduction on how DQ works. So DQ is a data structure. So we can add elements to the front of the queue, and we can also add elements to the back of the queue. So basically here all the operations like push, pop, front, back are O1 cost operations. So what we will be doing over here, that first we will be adding, so the first element will be directly added to the DQ since there is nothing, and while adding the second element, so here we are trying to maintain a monotonic sequence. So monotonic sequence here refers to a like continuously increasing or decreasing sequence. In case of sliding window minimum, we will prefer to have a continuously increasing sequence. So basically here we have 601. So now before pushing 35 to the back of the queue, we will first check whether the remaining elements in the queue are greater than 35. So basically not the remaining elements, that the backmost element. So now this is the front and back, so it is the same element. So the element at the back, is it greater than 35? If yes, then we will just pop this element. So now the double-ended queue looks something like this. It has only element 35 in it. Now when we will insert 45, we will check if the last element or if the back element has is greater than it. So here it is not greater than it, hence this will be our DQ. Now coming to 304. So yeah, when we start checking for 304, first we will again before pushing 304 into this, we will see whether like there exists a greater element at the back of the queue. Also, it is now quite obvious from this that the front element of the queue will be our required minimum. So for 304, as you can clearly see, the minimum out of these three was 35, and this is the front element of the queue. So basically what we will be doing is that we will be calculating dp of I is equal to a of I plus dq dot front. So this will be our formula for calculating the dp of I for elements after k. Now here since there were no elements greater than 304, we inserted 304 in the DQ. Now for 449, when we insert first, we have to check if the first element, that is the k minus that I minus k minus 1th element. So if this is I, we need to make sure that the I minus k minus 1th element is out of the DQ. So first we are checking if the front element is not 601. So here it is not 601. Hence we will directly go to the next step, that will compare all the back element with 449. And if it is greater, then we'll pop it out. But since there are no greater elements than 449, we'll just write 449. Now coming to 452, it is again the same. So for 449 again we can calculate the DP. So for 449 again the minimum will be 35. Now for 452, first we will check if the I minus k minus 1th element is still present, and yes, it is still present in the DP in the double-ended queue. So we will just pop out this element, and now we will just check if the remaining elements are lesser, or sorry, not remaining, or the last element is lesser. So yes, it is lesser, so 452. And again we can calculate the dp for 452 by taking dq dot front, but here dq dot front is 45 this time. So the dp will be so the dp of I for 452, it will be 452 plus 45, and similarly you can do for all others. So here basically our overall complexity of our algorithm will be O of n, and this is the best that we can achieve, and this is achievable by using DQ. If you had used a segment tree, then you would have to calculate a range minimum. So range minimum would have been a log n operation, and hence the overall complexity would have been n log n. So yeah, I think you got the gist of the DQ, and now let us quickly proceed to the C++ implementation. So starting off with the implementation part, let us first take input the two integers n and k. Then we will take input the array AI, where AI is the number of minutes chef has to spend each day to do his homework. Now let us quickly handle a corner case. If n is equal to k, then we will output 0, as it is obvious that he can just hack the records all of the days and he will just not do any homework. Now we will proceed to the main part of our implementation. Let us get into the vector. So we will initialize a vector dp of size n, and we will also initialize a dq for pair of int comma int. Now let us quickly check it out. So here dp is equal to a of I for the first k plus 1 elements we are doing. So we already saw this. So dp will be dp of I will be equal to a of I for the first k plus 1 elements. Now we will just check the normal thing that I did while using dq, that we check that if the back element is greater than dp of I, then we will just pop the back element, and we'll keep doing this until we reach an element that is no longer greater than dp of I. And after doing this, we will push dp of I comma I in the DQ. So we are pushing I so that we can keep track of the index. So now with doing this, we ensure a monotonic sequence. Now coming to the next for loop. So we have the for loop from I is equal to k plus 1 to I less than n. Now here first what we do is we check if the I minus k minus 1th element before this element is actually present in the DQ, and if it is present at the front of the DQ, then we will just pop front. So we will remove that element from the DQ because as you know, the front element is our minimum, right? So now we will just initialize this variable prefix of minimum, minimum prefix is equal to dq dot front dot first. So as I said earlier, that the first element is our minimum, so this is our prefix of minimum, and here we will calculate dp of I is equal to a of I plus prefix of minimum. Now we will just again check that before adding dp of I to the dq, we will check if the back element is greater than dp of I, and if it is greater than dp of I, we will just pop it. So this will continue until we find an element which is no longer greater than dp of I. So this again ensures that we have a monotonic sequence. Lastly, as we discussed, we will just take the minimum of the last k plus 1 elements. So this is the for loop for taking the minimum of the last k plus 1 elements in the dp, and we will just output the answer on a new line. So yeah, this was a pretty long explanation, but I think it was clear. And if you have any doubts, feel free to leave them in the comments. And yeah, thank you.